Is Richard Dawkins proving the existence of God after all? I think yes, on the basis of an argument by Richard Dawkins himself. There is an intriguing debate, TV debate, between Richard Dawkins and the Sydney Cardinal George Pell in the Australian Broadcasting Corporation. It is a TV debate in April 9th, 2012. I quote a most interesting moment of this debate, referring to the transcript in the ABC website. George Pell makes the statement that he, Richard Dawkins, continually talks as though God is some sort of upmarket figure within space and time. Now, from 450, 500 BC, where with the Greek philosophers, God is outside space and time. End of quotation. Richard Dawkins responds saying, "We are struggling. We are all struggling. Scientists are struggling to explain how we get the fantastic order and complexity of the universe out of very simple and therefore easy to understand, easy to explain beginnings. God, a creative intelligence, is not a worthy substrate for an explanation because it is already something very complicated, and it is no good invoking Thomas Aquinas and saying that God is defined as outside time and space. That's just a cop-out. That's just an evasion of the responsibility to explain. That's just setting out what you want to prove before you even started." So, Dawkins' reasoning in this statement has this logical structure. Premise A: existence outside of time and space proves that God exists. Premise B: there is no such a thing as outside time and space. Premise C: defining God as outside time and space is just setting out what you want to prove, begging the question. So you see that from this statement, Richard Dawkins actually assumes premise A, that existence outside of time and space proves that God exists. But he states there is no such a thing as outside time and space. Therefore, we have no proof of the existence of God by stating that God is outside space and time. Well, today we have from quantum physics the evidence that there is such a thing like outside time and space. The research on quantum non-locality proves that quantum phenomena come from outside space and time, from outside the space-time. We have experiments proving this. So this means that premise B in Dawkins' argument fails, and therefore premise A prevails. I would like to say something more about this point that quantum experiments prove that quantum phenomena come from outside space and time. Quantum physics is not only a description of the visible world around us, of the material world around us, but it is also an explanation in terms of influences and agency coming from outside the space-time. This has been proved by experiments, among others, 2 experiments I propose that have been realized at the University of Geneva in 2001 and 2012, last year. And these experiments, I have presented them in many articles and essays and also in other YouTube videos. But I would like to refer to one of them briefly here in order to explain what does this mean, influences coming or phenomena coming from outside space-time. The experiment actually was the first time presented by Einstein in 1927 in the 5th Solvay conference in Brussels. And it was a Gedanken experiment, a thought experiment, and by means of which Einstein wanted to refute quantum mechanics. Einstein proposed the experiment like this. We have here electrons impinging on this screen, and in this screen there is here a small opening. And according to quantum mechanics, after this opening, the electrons behave like waves, and this means they are propagating like spherical waves towards this photographic plate. It is like, if you wish, like an array of detectors. These waves are not material waves, but we say in quantum physics, probability waves. So this means that each of these detectors had the same probability of getting the electron detected. When Einstein, this was an argument proposed by the so-called Copenhagen interpretation, Niels Bohr, Werner Heisenberg, Born. When Einstein heard this interpretation, he was quite upset because he said, here we have a kind of action at a distance. This means that if this detector clicks, all the others know immediately that they must not click. So there is a non-local coordination between all these detectors. Even if these detectors are far away from each other. So Einstein say this is in contradiction with the principle of relativity, because it requires that there is a coordination here between this detector, for instance, and this one going much faster than light. So we have a contradiction with the principle of relativity. Astonishingly, this experiment proposed by Einstein in 1927 was never done till last year, and this is one of the experiments we have realized in the lab of quantum optics in Geneva. We have used a different setup, but essentially is the same. Here we have a source of light, a laser source, emitting particles of light, emitting photons. These photons impinge in this half-silvered mirror, and then after the half-silvered mirror, there are two paths. When the transmitted path reaching detector A, Alice detector, and the reflected path reaching detector B, Bob's detector. So, according to quantum mechanics, it is not so that the photon, one photon is traveling this path and another photon is traveling this other path, and so you get 50% of the photons here and 50% of the photons there. No, that is not the explanation by standard quantum physics. Standard quantum physics states that actually the photons appear only at the detection, and each detector gets the information at the same time because they are about at the same distance. They get the information about that a photon was emitted, about the energy the photon carries, about the paths, about the half-silvered mirror, and so each detector knows that he has to fire 50% of the times. And this detector knows that he has to fire 50% of the times. But each time, only one of the detectors clicks. So this means that there has to be a coordination between the two detectors. Even if we set these two detectors quite far away from each other. Without the coordination, you would have this funny situation. You can have here Alice detector, and here Bob detector. If there is no coordination, each detector knows he has to fire 50% of the times, but regardless of the other detector fires or not. So you have the situation, you could have that Alice detector fires, we put here 1 for one count, and Bob detector then doesn't fire. We put 0. Or, conversely, Alice detector doesn't fire, and Bob detector counts. But, since each detector fires regardless of the other fire or not, you could also have the situation where both detectors make a count, and also the situation where none of them counts. You see, this is if there is no coordination between these two detectors. And the amazing thing is that in certain case, even when the source is emitting only one photon at a time, you would have the situation where sometimes with one photon emitted by the source, you get here 2 counts, and other times you get no count in Alice's detector and no count in Bob's detector. So these 2 cases here in red would violate the conservation of energy, because here with one photon, you get 2 counts, double of energy. And here with one photon, you get no count, no energy disappeared. You have conservation of energy in the average, but not in each single quantum event. So you see that for having conservation of energy, you need to have this coordination between Alice's detector and Bob's detector. And since we can put these detectors quite far away, then this coordination could not be explained by signals traveling bound by the velocity of light. The experiment in Geneva consisted in putting exactly these 2 detectors quite far away and checking whether we get this situation or not. And the result is that actually we only get these 2 cases here. And that there was a perfect coordination between these 2 detectors, with these 2 detectors quite far away. We didn't get this case nor this case one. So we prove that this experiment proves, in summary, first, that since non-locality at detection is at the core of interference experiments, then this means that an experiment like that of Michelson-Morley, which is the observational basis for relativity, this experiment requires quantum non-locality. So this means that relativity and quantum physics not only are not incompatible with each other, but they imply each other. You cannot have the one without the other. Second, and that is most important, the most basic principle ruling the material visible world, the conservation of energy, requires quantum non-locality, requires influences coming from outside space and time. So you can say the material world would not function without this non-material principle, without this agency coming from outside space and time. And third, since you can say light reflections happens all over the world, in a glass window, in a water surface, then this means that non-locality happens everywhere and continuously. In summary, in quantum physics, we have reached a point where the responsibility to explain obliges us to accept agency from outside space and time. If speaking about outside space and time is a cop-out, then quantum physics is a cop-out. We can say then a bit that if we put together Richard Dawkins' reasoning with the results we have, with the evidence we have from quantum experiments, the consequence is that God exists. So in this sense, I think that Dawkins' argument is, in a sense, proving the existence of God. Well, I would finish saying that for discussing one of the biggest questions of human knowledge, of human history, the question of the existence of God, the evolutionary biologist Richard Dawkins and the theologian Dawkins-Pell are both referring to the concept of outside space and time. Thereby, the excellent debate between Dawkins and Pell, Dawkins versus Pell, this debate illustrates the cultural relevance of the research on quantum non-locality. And I think it would help that both the theologians and the biologists get informed about what is going on in the today's experimental research on quantum non-locality. Thank you very much.